Hello, am I audible?
Yes, sir. Good morning, sir.
Okay, no.
Good morning, sir. You are audible.
Yes, okay, fine. Okay, so you can start your questions.
Hello.
Yes.
Sir, there is a concept called matrix of a reflection. That matrix of a reflection is not being talked about in the lecture.
Yes.
So can you put some light on that?
No, like, see, it's basically
Hello.
yes.
So there is nothing regarding matrix of a reflection in the lectures, which are there is in the solve with us. There is something that
Yeah, so the thing is,
square.
no, the thing is there is no general form for matrix uh, of reflection. Okay, so you have to find out explicitly like how you are doing the reflection, like with respect to which axis and how actually you are doing the reflection. So for each different cases, you have to find the different matrix. Okay, so for example, for rotation, basically with respect to per se rotation, you have some specific matrix, right? Say this, if you want to rotate a vector, for example, this is my vector x, and you want to rotate by an angle theta, say.
Okay.
So what question is discussed?
Like matrix of reflex.
Oh, okay, sir.
So probably this is the matrix. So yeah, so that is basically there is a matrix which actually you can talk about reflection with respect to some angle theta. So similarly, like for matrix of reflection, you have different types of reflection. Like if you reflect, for example, if you have point x comma y, and if you reflect about x-axis, maybe say you get minus xy. So for
So
this
what
one,
will be the matrix?
yeah, you just find out the matrix, like what matrix if you multiply with
So
x,
it should
y.
be x minus y, right?
Sorry. Yeah,
So
yeah,
the
yeah. Sorry. Yes, yes. Yeah, so you need to find the matrix, right? What matrix if you multiply, you will get x equal. What matrix you if you multiply with xy, you should get x minus y. Okay, and similarly, if you reflects with respect to y-axis, then you will get something minus x minus y. So similarly, you need to find the matrix, which matrix if you get if you multiply with xy, so that you will get minus xy. So different types of reflection have different so it's depend on how you are reflecting your vector. So accordingly you have to find out the corresponding matrix. So there is no such called reflection matrix. Okay, it's depend on how you are reflecting.
So in the first one here,
Hmm.
xy reflecting along the x-axis, the matrix will be what? I mean, it will be just, I mean, 1 and 1 0. Okay, 1 0.
This is basically what you want some matrix with. Yeah, so basically what this is basically 1 0, this is 0 minus 1, right?
Yes, right, right.
Yeah. So yeah, so it's depend like how, like you first you need to find how what is your like what is your reflection, okay, and how it's converting a point in R square to some other point, like how it's converting a point in R square. Then only you can find out the matrix of the reflection. Okay, so
And there is a property mentioned about the matrix of reflection, that the square of a matrix of reflection is equal to the matrix itself.
yes.
So
that
that
is,
also has the.
no, that is quite obvious, right? So if you so this is a point, right? This is a point. So if you reflect this point along with respect to x-axis, you will get this point, right? And
Yes,
again, if you reflect this point, so this is your point A, this is your point B. If you reflect A with respect to x-axis, you will get B. And again,
right.
if you reflect B with respect to x-axis, so you will get A, right?
Right.
So applying twice, you are coming back to your original point, right?
Right.
Yeah. So it's quite natural, like, yeah.
Okay. So this okay. So the same. So that same matrix will work for the opposite case also.
Yeah. That is what you mean by a square equal to, like, yeah, basically.
Okay. Actually, nothing was mentioned regarding
No,
this
sir,
in the
not a square
lectures.
equal to a. That is basically a square equal to identity.
No, sir. A square equal to a. It is written.
No. That is projection matrix. Okay.
So that's what projection only. Sorry, not reflection. Projection matrix. So there's nothing mentioned regarding projection matrix also in the lectures.
No, it is mentioned, like I guess, sir. Yeah, so he has done a lot of things about projection linear transformation.
He has given the formula for projection,
Yes.
but he has mentioned nothing about how we can make a matrix out of that projection.
No, that is okay. Like so that is basically, it's quite more or less. It's basically, if you have a projection matrix, then it projection linear transformation, then it will clear, like you can see this will satisfy this condition.
Sir,
So
in the first one, a square equals to I, that will be A transpose A equals to I, right?
sorry.
That you are talking about A means the R theta, right, sir?
Which one? Here?
The first one you wrote A
No.
square is.
This is reflection matrix. It's not orthogonal matrix. Okay.
Okay.
So basically he actually basically he mentioned, if you see, he mentioned that so when it is a what projection matrix from P to W, right? So T of W is equals to W for all W in W, and he defined something called W of, which is basically the vector in V, such that all the vectors in V, such that V of W, inner product of V and W is basically 0 for all V in V, right?
So what is the symbol W that this one?
Yes, how it is spelled, sir?
Sorry?
What is the
How
symbol?
it is spelled that?
V of. Okay. Or maybe you can say that the complement of W.
So this W of or V of whatever, it should be actually the set of all vectors which are perpendicular to V, right? Which are perpendicular to W, right?
Yeah, that is what, okay, yeah, sorry. Yeah. So,
So is that sir first equation is correct? TW equal to W or TV equal to W?
no.
So what is the difference, sir? Because normally we say TU equal to V, here you write TW equal to W.
No, W is basically just subspace of V, right?
Mm-hmm.
So then I can talk about, T of W, right?
No, but in the translation mistake, from V you are getting W. So then how the TW, where is the V going? So I can take, so from this first expression, I can say I can take a vector from the V and I put the translation matrix on top of it, and it will
the
give
first,
W.
no. See, the first condition says that T of W is always W. If W is a member of W, okay, and then T of W is basically W. I don't know what, for example, if I pick a arbitrary element of V, then I don't know what is T of V. Okay, then I have to do it. I don't know. Certainly it's a element of W, but I cannot tell you what is the precise image of a element of V.
Yes, sir. So then what is the use of this translation matrix? Because I know that everything is W is a W.
Yes.
Okay. So you are basically saying that, so this is a projection matrix. So you are saying if I let us take a concrete example. Suppose I am in a R2, Now I take a vector space. Now in this vector space, you are saying, can you give a concrete example? Actually, I am not getting it actually.
No, okay, I'll come to example, but I don't see what is the problem over here with this condition.
I have no problem. I am saying that when there is a transformation matrix is there, in the transformation matrix, you normally give the domain is your V. Here, according to this notation. Okay, and you get I shall get the W. But here you are saying that although my domain is V, but this condition is only satisfied if I take something in the W.
Yeah, this condition is only for a because T is a projection from V to W. Okay, so when you are projecting,
So here T is not linear transformation, is it? That is why.
Obviously T is a linear transformation.
By
So
T,
the matrix of this linear, matrix of this linear transformation is the projection matrix.
Yes, basically that the matrix, see, the linear transformation will satisfy this condition. Okay, so if T square equal to 10, then basically your A square will also satisfy this condition. Okay.
Okay.
See.
So there is a question, practice assignment.
Just a minute. Okay, so so basically I'm projecting the vectors I'm projecting all the vectors of V on W. Okay, so so I'm projecting all the vectors of R square on x-axis, right? So if there is a point on x-axis, okay, so then what will be the projection of that point?
That will be on the x-axis.
That will be the same point, right? So that is what I have written here.
Okay.
If W is a point in W, then the image will be the same element.
And how can you tell me, give me an example for WT equal to this second condition?
Yeah. So So the W, I'll do a complete example. So how actually is so what is basically going on here? So W pop is basically the orthogonal complement of W, and the image of T of W is 0. Okay.
So W pop consists of all the vectors which are perpendicular to this vector space W.
Yes. So in particularly here, the
yeah.
so if my W is x-axis, then W pop is basically y-axis. And
Yes, yes.
as you can see, the projection of y-axis on x-axis. See, if you pick any element of x-axis, a y-axis, then the projection of that point on x-axis is 0. Okay, that is what I have written here. Okay, if you take the orthogonal complement of W, then that image is basically W. So now using these two information, you can say that actually T square equal to. Okay.
How, sir?
Yeah. So.
Okay. Right.
So you can write any element of V. So V is basically what? W direct
Plus null space.
Plus W of, right?
Yes.
Right. So what is T of V? T of V right? So this is nothing but T of W plus T of W dash. And I know T of W pop is basically 0. So, and W dash is an element of W pop. So that means T of W dash is 0. And the first condition says T of W is basically W. Right?
Yes.
So again, if you apply T, what you will get? T of W. And again, T of W is W, right? So this is so this is nothing but T of B, right? T of B is W. So basically what we got? T square is T. Okay. So that is.
So what will be the projection matrix for this particular?
Then yeah. So then you have to take basis, and then you can construct the projection matrix. It's basically what you will get, some kind of. So if you take a basis of W, so for example, say say
1 0.
Dimension of W is what? Say 2.
1. X-axis, so it will be 1.
Yeah, I'll come to some particular example. So say dimension of W is 2, and dimension of W pop is also 2, right? Let's say. So then so consider a basis which is basically W1, W2, and W1, W2 is basically a basis of, it's a basis of W, and W dash, W1 dash and W2 dash is a basis of W pop. So then W1, W2 and W1 dash, W2 dash is then it is a basis of B, right? So I want to now construct the matrix representation of T with respect to say this basis. Okay, so with respect
So sir, is this statement is always true? So if I take a subspace W, and if its basis is W1 and W2 and its null space is basis is W1
No,
dash
no. Here basically I am using this fact that V is W plus W.
Okay.
Okay. Nothing related to this null space or image, nothing like that. I'm just using this fact. Okay. Since V is basically W plus W pop, if I pick a basis of W and if I pick a basis of W pop, and if I will take the union, then that will give me a basis for V. Okay. So then I know like T of W is W for all W in W, and T of W dash is 0 for all W dash in W pop. Now you can compute the matrix representation of T with respect to this basis, right? You will get some identity matrix here, and rest entries will be 0. So let's take an example. Say, so let's say it's a map from R square to say W. So what is my W? It's W is basically x-axis. So W is x comma 0, where x is in a set of real number. And how the map? So what is the algebraic expression for this one? T of xy is nothing but
x0.
x0, right?
Right.
So as you can see, if I pick a element in W, if x comma 0 is in W, that means T of x comma 0 is precisely x comma 0. That means T fixes all the elements of W. Okay, that is what I have written here. Okay.
Right.
And what is the orthogonal complement of W? What is W pop?
Y-axis.
Basically set of all elements in R such that
R square, sir.
R square such that A comma B is perpendicular to 1, 0, right? Because W is basically span of 1, 0. If A comma B is perpendicular to 1, 0, that means A comma B is also perpendicular to alpha times 1, 0 for all alpha in R, right? That means A comma B is perpendicular to span of 1, 0, which is W. Okay, so writing A comma B is perpendicular to W is same as writing A comma B perpendicular to 1, 0. Okay. So then W pop is basically A comma B in R square such that A equal to, so if I calculate the dot product, then what I will get? It's precisely A equal to A dot
equal.
It's precisely A equal to 0. Okay.
Sir, the second element will be 0, no, sir?
No, this is 0, right?
Right.
So then what? If you multiply, so you have to multiply A with 1 and B with 0. So then you will get A is precisely 0, right?
Right.
So then this set is nothing but 0 comma b,
0 comma, right.
b in R square, or b is arbitrary.
Y-axis.
Yeah. So this is precisely y-axis. Okay. So as you can see, the image of the y-axis, if you pick any element of y-axis, then image is precisely 0, right?
So for this, if we want to make the, so we take a standard ordered basis for R square and take the image of that standard ordered basis, and similarly we are forming for any transformation. That way you have to make the matrix, right, using standard ordered basis.
You can pick any basis, and with respect to that basis also you can, but yeah, certainly it's easier if you do it for a standard order basis. Okay.
So, sir,
Sir,
can you say
there is this?
Go ahead.
On.
Yeah. So, sir,
no,
can
actually.
you? Sorry.
Okay. So, okay,
Sorry.
Siddharth, you say.
No, actually, if he has a doubt on this particular thing which you have explained, let him go ahead, because I am going to ask a question on practice assignment 8. So it is similar to, the concept is the same which you are explaining here.
Okay. So before that, you have checked the solution, right?
Which one? Practice assignment.
Huh.
Sorry, sir, I have not gone through but I have some doubts regarding this question, so I was asking.
Okay, so in the meantime, I'll suggest you please go and check the solution. Okay, once.
Okay, sir. Okay.
Yeah. So otherwise, we can always discuss that question.
Okay.
Yeah. So Amitabh, yeah.
Yeah. So, sir, maybe I am asking a very trivial question. So, if I calculate the A of these things, so because here a lot of other terms is coming into the picture, like EU and other things is coming into the picture when we write these matrices. So, can you give an idea what is this? So, particularly, I tell you one of the question, the activity question, then that will be useful. Okay, give me a second. So activity question 8.5, question number 7.
Yeah, that is basically, it's a calculation based question. You have to find.
No. So here my problem is that what is EU, what is B, it is given. So maybe I am not able to understand that.
No, the matrix representation is given, right? The matrix. So with respect to some basis, okay.
So what is EU? Actually, what is EU? Orthonormal basis. Yeah, go ahead.
So TU is basically, it's a matrix representation of T. With respect to some, certainly it's mostly with respect to some orthonormal basis. Okay.
So, sir, maybe I am asking a very trivial question. So, sir, if I take this matrix, can you open the 8.57? Then I can ask you the question.
Yeah. It's you have with you, or you want me to share the screen by
share the screen, then I can.
Okay, then just a minute. Give me a minute. Yes, it's feasible, right?
8.57.
Yeah.
Yes.
So yeah. So in this question, so U is an you are saying is a basis is given. Okay. So from here I can calculate is it a orthonormal basis or not. Okay. So my question is that here the question is giving that T is an orthogonal transformation or not. So what is the relation of U and T? Is it the same relation? Or so can you explain what is the relation between the U and T?
Yeah, so basically, if U is a orthogonal matrix, okay, so then you can say that T is a orthogonal linear transformation. Okay.
But what is the relation between this? Is the T equal to U into V?
Not necessarily. Yeah.
So normally when we before this for 6th and 7th week we get a matrices like this.
If certainly if see the thing is if you are getting U with respect to the standard order basis, right? Then certainly T of X is basically U times X. Okay. If you are getting with respect to a standard order basis, okay, but if you don't have some standard order basis, maybe some you are computing the matrix matrix of the linear transformation with respect to some different orthonormal basis, okay, then certainly you cannot say that T of X is basically U times X. Okay.
But here it is a standard normal basis, can I say? Because it is nothing is said.
Nothing is mentioned, yeah. So so basically it's basically with respect to, you can say that with respect to some orthonormal basis. Okay, that is what you can say.
So I cannot build direct correlation between the T and U. T is a function of U, but I don't know what is the relation between the T and U.
Yeah, true. Yeah.
Okay,
so
and
just like the whatever you have done in your normal linear transformation, you don't, if you have a matrix, right? So you simply you cannot say that T of X is basically A times X until unless you are not getting that matrix with respect to the standard order basis, right? Yeah. So similar thing happens here. Okay. Until unless you are not getting the matrix of the matrix with respect to the standard order basis, you cannot say that T of X is basically equals to U times X. Okay. Once you know, okay, I'm computing the matrix representation with respect to the standard order basis, then I can blindly say that T of X is basically U times X.
So here actually for the fourth option, sir, we have to calculate it, na? Or then only we can know, na?
Everything you have to compute manually. Okay.
So how I yes. So how I check that U is an orthogonal transformation? So should I take the column vector and make a dot with everything? Well, like I
no, to say that U is basically orthogonal transformation, or you need to check that whether U is a orthogonal matrix or not. Okay.
So that means A dot A transpose equal to I, that property?
Exactly. Yeah. A times A transpose is basically. So shall I stop sharing my screen? So now it's clear.
Yeah.
So thank you. So this for orthogonal matrix, any orthogonal matrix U, U transpose should be equal to U inverse, right?
Yeah, U basically U into U transpose should be identical.
Equal to I. So U transpose should be equal to U inverse.
Yes.
Which means that U should be a invertible matrix.
Yes, certainly. See, if your columns of the matrix are orthogonal, okay.
Okay, then it will be.
Then basically this is a basis of Rn, right? So if you have n vectors, so it's a basis. So then from there itself you can say that this matrix is invertible. Okay.
Right. So, sir, can we go to this question, practice assignment 2, question 2, because the solution is given here, but I am not able to understand the solution. I thought the answer was S, but actually the answer is P, statement P.
Which one? Can you tell me question number?
Practice assignment 8, question number 2. I thought the correct, I thought the true statement is S, but actually it is P. So the solution which is given here, I'm not able to understand that solution. First step I was able to understand.
No, you have four statement in question number 2, right?
Yes, yes.
So,
out of that, I thought the S statement was correct, but actually it is the P statement which is correct. So
P statement is correct. Yeah.
So
yes.
I'm not able to understand how we can derive that this P statement is correct.
No, still I'm not getting, like, which one you are asking. So you are fine with statement P?
No, I'm not able to derive how this P statement is correct. The proof for this P statement, correct.
Okay, so you are saying how I'm getting this. So how actually we are proving that statement P is correct, right?
Right.
That
and
is
S
what
also. And S also.
Yeah, that is what you want to know.
Yes.
Okay,
and S
okay.
also.
Yeah, okay, that is fine. So first of all, I just want to know your question. Okay.
Right.
Just a minute. I'm just taking a picture so that I can write it screen.
Sir, I have a doubt related to the notation, sir.
Yes. Yeah, so now it's visible, right? Screen?
Yes, yes, it is visible.
Okay.
Sir, I have a doubt related to one of the notations, sir.
Yes.
Sir, in week 7, sir, like while studying dot product and inner product, sir, like we have used two vertical lines, right? So how to pronounce that? Whether they are double module?
Sorry. This one, right? Hello. Am I audible?
Yes.
Yeah, this you pronounce as norm. Okay, this is just a map. Okay. Yeah, so this you simply just pronounce as norm. Okay. Okay, so if you see the
Sir,
thing,
I had lost the connection. Sorry, sir. I rejoined again. So my question was, sir, yes, sir. I was talking about these two vertical lines.
Yeah. This is how you this is basically you call it as norm. Okay. So
what does it represent? It represents the length of the vector, or what does it represent, sir?
yeah, that is a different question. What does it represent? It's basically represent the length of the vector. Yeah, true.
Length of the vector, right?
Yeah, yes.
So we can also call it as double modulus, right?
You can call whatever you want, but in general we call it norm. Okay, so that is not a big thing. Yeah. So it's basically it's a norm map. So as you can see, the way we have defined the norm map is basically using this symbol, right?
Okay. So we have to call it as a norm.
Norm map. Yeah.
So it basically represents the length of the vector, which is
yes. In generally, we don't use it everywhere. When we are talking about norm, we use this symbol. Okay.
And are we supposed to put arrow also, sir? Above that, are we supposed to put arrow also?
Above what?
Like this, vector. We will write vector inside.
No, in generally, so from the very beginning, we are not putting any arrow on a vector, right?
No, I was asking in general.
No, in general, that basically you do in physics.
Okay, sir. Thank you, sir. Thanks for clarifying my trivial doubt. Okay.
Yeah, it's fine.
So will you also be like clearing, like doing the theory part for this week, or will it be only a doubt clearing session? Like,
see, it's a doubt clearing session, but anyway, I have discussed some of the theory from the lecture, right? So here.
Can you discuss in sequence the theory?
Sorry.
Can you discuss the theory in sequence for this week? Yes, sir. That will be better.
Okay, so basically what I have to discuss then. So first is more or less. So there are two things, right? One is in more whatever. I think it's basically projection and this finding a orthogonal basis, right? Ortho, or maybe say orthonormal basis. This Gram-Smith, two things. So you basically want me to discuss these two things, right?
Yeah, and the rotation as well, finally.
Okay, rotation matrix. Okay. Okay, so
Yes, this practice assignment question, sir.
Yeah.
Or...
So just Mohan, just let me finish this one. Then I can go according to your suggestion. Yeah.
Okay. Okay.
So So okay. So the thing is, like in there actually I have mentioned that a linear transformation T is a projection right?
Right.
So so if I can I can show that this map, whatever it is given over here, P of W, no, P of, so it's given that P of W1, right?
Right.
It's a map from V to W1.
Right.
Which since W1 is a subspace of W1 is a subspace of V, so even you can think of it as a map from V to V also. Okay, so just the we have some. I'm taking just two different code only. Okay, so more or less the maps are same, and it's given that P of W2 is also a projection, right?
Right. Right.
So then, by this property of the projection, so I can write this one, right?
Right. Right, sir. Yes, this is clear, sir.
So then you are done, right? So
how come, sir?
So what you want? You want this to be P of W1. You want this. You want to show that this is a projection, right?
Yes.
That is what you. That is what option S P is saying, right? You want to know whether this map is a projection. So under what condition this map will be a projection map, right? So for that, what you want? You want the composition of this map with itself should be the
same, right?
Same map, right?
Right.
So then this you can write as P1.
Yes, this
square.
step I was not understanding. So how come?
Yeah, so this is basically the map is yeah. So basically we are using this fact. Okay, that is what I guess I have mentioned in here. So basically a linear transformation is a projection if and only if it satisfy this condition.
Yes, this is clear, sir. But how you are writing this statement which you are going to write here, this statement which is given in the solution also, this statement I was not able to understand. How from this previous statement we have come to this new statement, sir?
Which one?
The one which you are going to write now.
Okay.
This statement is this statement I have understood. Now the second statement which you are going to write, this statement because this is a composition.
Yes.
So how we can write? How we can use the multiplication for this composition?
Not multiplication. I'm doing the composition, right? And
okay.
And again, see, this is a composition, right? So what I am doing, I'm basically composing this one with this one. Okay. Then, so I'm basically using the distributive property and as well as the composition property.
So for composition, distributive property will work, sir?
Yes, that certainly it holds. Okay.
Okay.
So for maps, yeah. Until unless you have some notion of addition in your domain.
Okay.
So this is nothing but P1 composed with PW1 composed with PW1, and again PW1 composed with PW2. PW1 PW2 composed with PW. Okay. And after that, I'm using the fact that this is from here, this is nothing but PW1.
Right.
And this is nothing but PW2.
PW2. So this middle portion is 0.
Yeah. So then middle portion is 0. So this map is a projection map if and only if this middle portion.
Why?
So for composition, this distributive property works. This I was not able to understand how.
I'll suggest you try to. This is basically a basic calculation. So you try to do it. You try to do it manually. Okay. You can obviously you have to use the what this property. Okay. So how actually we have defined this composition and this addition. Okay, you have to see what is this PW1 plus PW2 of some vector is what? PW1 of V plus PW2 of V. So yeah, so then you try to compute manually. Okay, you can get it.
Okay.
So okay, so then yeah, so I'll suggest you try to do it. Okay, if you are facing problem, then we can do it. Okay, it's not yeah, so yeah, you don't have to do something else. It's basically some manual computation. Okay, so the next statement is statement Q. Statement Q is true, right? It's basically it's given in the question.
Q and R, I could understand. S is similar to P, I think. Statement S is similar to P. Statement
yes, but,
S, which
yes, yeah, but it's not. It's in generally it's PW1 and minus PW2 is not a projection. You have
right.
you need to put some condition, just like in the statement P. So what basically we have concluded that this map is a projection map if and only if this part is 0. Okay. So
right.
So similarly, you can put some condition on PW1 minus PW2. So to make that map to a projection map. Okay. Otherwise, in general, you cannot say that I guess this map is a projection. Okay. Okay. So next, I guess I'll discuss about how you can compute projection of a vector on some arbitrary vector subspace. Just a minute. So okay. So any other suggestions? So where I should start from where I should start explaining the concepts?
Sir, you can start from the projection, sir. Okay. Basics of projection, maybe.
Yeah. Okay, so okay, so I have a vector space. So V is a vector space. and obviously with respect to some inner product. And W is a subspace of V. So if I have an element in V, so how I can know the projection? So if I project a vector V, so maybe say W on W, so what will be the image of this element? So what will be the image? So I'll denote the image by projects PROJ W V. So I want to know about this element. So how I can compute this one? This is what we are basically doing probably in lecture 2 or 3. So so the first thing is you need to find a orthonormal basis of W. Okay.
So there's a small doubt, sir.
Yes.
So if W is subset of V, that is
Subspace
subspace of V, then I was thinking that it will only be a projection of W on V. So V is the super space, like so to say.
Yes.
Right.
Yes.
So, but here we are saying we are saying projection of V on W, right? Yeah.
Yes.
So that is the conceptually I had a confusion. I thought only the bigger space would be the one where we can project the subspace.
No. For example, see, the thing is in R square. Okay. So you can project an element in X, right? In X axis on X axis, right? Also,
so
you can
drop a perpendicular on X axis. So
yeah. So that is, see, the projection is basically what it's giving you it's equivalent to. So what we are doing here, we are finding a vector in W. Okay, so we are trying to find a vector in W such that the distance between this point V and W is minimum.
Okay. I got it, sir. Because we can project the point.
That is actually in more or less that is the definition of projection.
So, sir, when you are projecting V to W,
yes.
W of W will be always less than V.
Sorry.
When you are projecting V to W,
yes,
the dimension of W will be always less than V.
It's not like that. Only one condition is given, that W is a subspace of V. Okay, certainly it can be a proper subspace of V, or also it can be V.
So it could be same subspace. Same.
Yeah, see, certainly if W is V, then the projection map is basically the identity map, right?
Okay. By itself.
Yeah, it's basically the identity map. So if I will project a vector, of R square onto R square, so then see, basically it's saying that if I project a vector of X axis on X axis, then I will get the same thing, right? So similarly, if I project a vector V onto this vector space V, then I will get the same thing. Okay, so the projection, if I'm talking about the projection map from V to V, okay, so then this map is basically the identity map.
So can we conclude that every projection is onto It may or may not be 1, 1, but it is
it's
always
certain,
on 2.
okay, it's 1, 1 if this
it's the identity map.
It's W is basically V. Yes.
Right. It's always on 2.
Yeah,
all projections.
It's always on 2. It's always on.
Right.
It's basically as you can see, T of W is basically W. Okay. Yeah. So okay. So what? Okay. Yeah. So projection map, whatever that defining this may say V to W. So this map is always subjective. Okay. So yeah.
Then we can also say we are taking the dot product, right?
Sorry.
By projection, can we say that we are taking the dot product?
No, we are not taking the dot product. Like it's basically we bunch of dot products. It's not a single dot product.
Yeah, basically you're doing it over the space. That's why every coordinate.
Certainly, it's not a single dot product. Yeah.
Not a single dot product, but
yeah. So yeah, that is true. It's basically some linear combination of bunch of dot products. So, okay. So my aim was to find a projection of a vector V on W. Okay, so the first thing what I need to do, I have to find a orthonormal basis of W. Say W1. I guess I have used this notation. Say V. Okay, let me use W1, W2, Wn is a orthonormal basis of W. Then the projection of the vector onto W is basically this I1 to summation I1 to N, this V. So whatever, so I want to find the projection of this vector, this V time V inner product with Wi times Wi. Okay, so this is basically what? V inner product W1 times W1, V inner product with W2 times W2, V inner product Wn times Wn. So this is basically the projection of the vector V on W. Okay, so the main, so basically what you have to find, so far the main task is you need to find a orthonormal basis of W. Okay, so once you have that basis, then this particular thing will give you the projects. Okay, so any question you want me to ask regarding this thing? Hello. So any doubt with respect to this?
Sir, can you explain this equation?
Sorry.
Can you explain this equation with some example?
Yeah, certainly I'll do bunch of examples. Okay, so don't worry about that. I'll try to do at least two 2-3 examples. So
yes, sir. So before we get to that, so looking at the equation, since we are orthonormal basis.
Sorry.
So since we are taking this as an orthonormal basis, right? And the equation. So before we go to that example, I just thought I clarified this. So here the inner product. So geometrically, we can say that V will be 90 degree normal to W1, W2, each of them, is it?
Sorry, V
will be normal to W1, W2, W3, like that, or the other way around. W1 is normal to W2 is normal to
W2 is normal to
V. W1, W2, W3, each of this will be normal to V. Like
no.
Geometrically, I'm saying.
No, that is not.
W1, W2 will be normal, but V is not.
V, yeah. So this is you can say that. So what basically you are saying? So this is V, right?
Yeah.
This is W, right? This is my space W, and this one is projection of V on W. So you can say that this vector. Okay, so what is this vector? V minus
projection of.
Yeah, you can say that this is perpendicular to W, like.
Okay, V minus projection of W.
Yeah, so this is basically perpendicular to W. In other words, if you take any vector in W, then inner product of V minus projection of V times W is 0.
Okay.
Okay, so let me do one question. So let's say just a minute. Let me check some question from. Okay, so let me do 8.3 question number, say 6. Okay, so consider a orthonormal, then which of the following vector? Okay, so first let me do question number 3, then I will do question number 6. Okay, because first I want to do with respect to some standard inner product, because question number 6 is more or less it's not so it's asking with respect to some non-standard inner product. Okay, I'll do that also, but okay, first let me do question number 3. So W is a subspace of R3, and some orthonormal basis is given for W. It's basically 1 0 0 0 1 0. So this is a orthonormal basis of W. So if I will try to write in terms of this,
I cap, J cap, K cap. No, okay, so 3 will be I cap, J cap, K cap.
What is okay? See, I cap, J cap. Okay, so this means A x-axis, y-axis, z-axis.
Correct.
Right? Yeah. This W is basically your
yes, sir,
XY plane. Okay.
Yeah, XY.
So this is my W1 and this is my W2. So the question in question it's saying that what? So how I can find a so how I can?
Question is this? Which question?
Question number 3, activity 8.3. Okay. 8.3.
3.
Yes, 8.3, question number 3.
Okay.
So basically it's saying x equal to 1, 2, 3, then which of the following vector in W whose distance from x is least? Okay, so that is what basically the projection is. Okay, so the projection of this vector x in W. So this is basically so basically the distance between this vector and this vector is basically minimum. Okay, that is what the projection gives. Okay. So what now I need to find? Yes.
One question over here. So the distance that you are talking about, that is the x minus projection of x.
Sorry.
The distance, the minimum distance.
X minus projection of x is a vector. It's not a distance.
Okay, but that is a perpendicular. That is the vector that the norm of that is.
That is distance. So that vector is perpendicular. Yeah.
So norm of that is the distance, and we are trying to minimize that, like visually. I'm talking about.
Yeah. So see, you have lot of vectors in W, right? So
yes.
So you have a vector here, you have a vector here, you have a vector here, you have a vector here. So I want to find a vector in W such that the distance between this x and that vector is minimum among all the possible distances, right? So you have, so if I take some W, say n, not W, it's not better, it's say W1 dash. Okay, so then this will give me some distance, right?
Yes, sir.
This will give me, if I'll take W2 dash, this will also give me some distance. Okay, so if I pick any element of W, and then there will be some distance between x and W, right?
Yes.
But this particular vector, this projection, this distance is always less than
I have like a small doubt. Here we are taking like only the normal, right?
We are computing the projection. Yeah, so
correct?
Yes, no, here we are computing just the projection. Okay, this vector.
So what I'm saying, angle between plane of xy plane and x is 90 degree, correct?
Angle between
xy plane and x vector, whichever that will be 90 degree, correct?
No, that is not correct. That is not correct.
How not, sir?
Sir, for the minimum vector, the perpendicular vector, right, which is you are using, you're calling as a projection of x actually. Just to be a minimum, it has to be the perpendicular to the xy thing. Then only we can say this is a minimum vector, because perpendicular length is always minimum. Minimum length among the other projections, sir.
Yeah,
also,
true.
I want to ask you this: projection doesn't have to be minimum, is it?
Sorry, projection. No, the projection. Sorry, don't have to be minimum in what sense?
You're saying the vector x minus projection of x, right? That is you're trying to minimize, correct?
Yes, that distance, yeah.
But it doesn't have to be minimum, right? It can be projection on any plane.
Sorry, what do you mean by that projection? I'm talking about a particular plane, W.
Okay, so if I'm taking a line, all right, and I'm projecting it over a plane, right?
You are taking a line, you are projecting on a plane, yeah.
So that distance, so you are saying that distance has to be minimum.
What do you mean by distance between a line and a plane?
The vector, there will be a theta, right, between them.
What do you mean by theta?
The angle between vector, the direction of V and the direction of the plane?
With respect to what? Like how you are computing the angle? With respect to what?
Angle between.
We'll have to. I think
No, that is a vector. It has to be a vector.
We have to drop a perpendicular.
So what do you mean by
from
angle
the
between
vector.
2 points? You are doing with respect to something.
Vectors, a plane is a vector and a line is another vector. So angle between
plane is not a vector and line is not a vector. A line contains infinitely many vectors. A plane contains infinitely many vectors. So what do you mean by angle? Like I don't see any concreteness in your question. Like,
sir, I can say 3 I cap plus 0 j cap plus 4 k cap, right?
Sorry?
3 I cap plus 0 j cap plus 4 k cap.
Yeah, this is a particular vector. It's not a line.
It's a plane, right? It's a vector also.
No, how a vector and how a particular thing can be vector and a plane simultaneously? How a particular thing can be a vector and a plane simultaneously?
Sir, can you just explain that projection?
No, this is a vector or a plane? Tell me, this is a vector or a plane?
Vector.
Which one, sir?
This
Vector.
1, 1, 2, 3.
Vector.
It's a point, right?
It's a point. It's not a plane, right?
No, it's not a plane. It's a point.
Yeah. So you are saying 1 I cap plus 2 j cap plus 3 k cap. So this is a point, right?
Yeah, it is a point. But I'm saying if I make the j as 0, right?
But it is also a vector, no, sir. This 1, 2, 3 is also a vector, right?
See,
apart from being
even if you make j to be 0, then what you are writing? 1 I plus 3k, right? This is also a vector, 1, 0, 3, right?
Yeah, and if I draw this, it will be a plane also. Correct?
Okay, I don't know how. No, this you are not making any sense. Like you have to. So when you are talking about a plane, then you have to give an equation of that plane. Okay.
Yes. You need two span of two vectors.
Yeah, maybe some. Yeah, so whatever, like span up to linearly independent vectors, or maybe something in terms of x and y. You are just specifying something, and if you are specifying, like you are basically giving a vector.
So can you scroll a bit up, sir? I just.
Yeah,
so then, like y is equal to 0 is a plane, right, sir?
Yeah, y equal to 0 is basically it's a xz plane.
Oh. Yes, sir. That's right. Yeah.
So projection.
So one more question in that.
Just a minute. Let him complete. Like maybe.
Actually, sir, the way I understand, every vector is in terms of like space, right? Because I'm a physicist.
It's vector. No, vector is inside a space. That doesn't mean that vector is a space. Okay.
No, space sense like physical space. I'm saying. So, trying to say 3 I cap plus 4 j cap will be a plane, right?
No. You first you try to think for a while, then we'll discuss. Okay, you try to think.
So this one. Sir, I have one doubt here in projection of x w minus x. The norm. Can you explain that geometrically? Like
which one?
Here.
Which one?
Within the norm, you have written no projection of x on w minus x.
This one, right?
Yes, sir. So what is that exactly? Projection of x on w minus
basically it's saying that distance of these two distance between these two vectors.
Can you scroll up, sir? That is substitute. Which one, sir? Which vector?
Okay. This is basically saying what? You have w here. This is your x. This is your w. Right? It's basically saying if I pick any point in w, say this w, then distance between x and w, it's always greater than the distance between x and projection of x.
Yes, sir.
That is what I have written here.
Yes,
okay. So it's basically saying if I pick any point in w,
yes, sir,
then distance between x and W is always greater than
yes,
the distance between X and projection of X. Okay, that is how actually projection, you can characterize projection by this. Okay, so it's a unique point. Okay.
Yes.
Okay, so let me yeah.
So I have a few conceptual doubts.
Yes.
So when we say V is an inner product space, do we fix the inner product? It is defined on just as we fixed addition and scalar product.
Yes. Inner product.
Okay,
so first you have to fix the inner product. Okay.
Okay,
so
sir.
with respect to different inner product, then the projection can be different. Okay.
Okay, sir.
So
and
the whatever
there will be
this visual things I'm giving, it's basically with respect to the standard inner product. Okay.
Yes, sir. So whenever we are given a inner product space, the inner product is defined. It may be so that in that very space we can define another inner product, but that is irrelevant as given that we are already given an inner product, right?
Yes.
Okay, sir. So there can be many norms that can be defined on V, but will all norms satisfy that the inner product of a vector with itself is equal to the square of its norm?
Sorry, I missed your question. Like what you were saying?
There can be many norms that can be defined on V.
Yeah,
but
that
will
is true.
will all norm satisfy the condition that the inner product of a vector with itself is equal to the square of its norm?
No, you are saying like whether I can define some inner product. Okay. So that using this inner product, I can get this norm, right? That is what you are saying.
No, sir. I'm saying that suppose we are given an inner product space V, then is it necessary that the square of the inner product of a vector with itself will equal to the square of its norm?
No, see that is okay. So okay, just okay. I'll come to this thing. Just give me some time to complete, because it will take a few minutes. Okay, let me complete it now. Okay, so the thing is, see, the thing is, you have bunch of inner product. Okay, so you have some inner product. Okay, lot of inner product. You have lot of norms. Okay.
Yes, sir.
So this is your inner product, and this is your norm. Okay, you have lot of norms on the same vector space.
Yes.
Okay, so using a norm, using a inner product, I can get a norm. Okay, using a inner product, I can get a norm. Right? This is how you define it, right? Norm of V.
Sir, I have a question regarding this too. So I was trying to prove whether it is a DOM or not. So I was able to prove the positivity and the homogeneity condition, but I couldn't prove the triangle inequality.
That you have to use Cauchy square. Cauchy square inequality. Without that, it's difficult to do.
Okay. Even if that has to be used, how do we put it? How do we satisfy the conditions of Cauchy squares and claim that it will hold true?
Okay, so you want to prove Cauchy squares?
No, I know the proof of Cauchy squares. I want whether how is it applied to this?
Okay, we'll come to that.
We'll come to that later. Yeah.
So actually, yeah. So it's basically it's for using a inner product, I can reach to some norm. Okay.
Yes, sir.
But the problem is there are few norm in this set which don't have any pre-image. Okay. So basically there is no element in this set. Okay, that maps to some norm. Okay, so for example, for this kind of norm, you cannot define it using a inner product. Okay, for example, there are few norms, okay, such that for that particular norm you don't have any inner product. Okay, so that V, inner product V, is equals to norm of V.
Okay, sir.
Okay, So basically what I was trying to say, using, so you have in this set, you have lot of inner product, in this set you have lot of norm, and using, see this, so each using each inner product I can get a norm, but there are few norms which don't have any preimage. Okay. So the thing is, whenever you have, so actually how in generally how you prove it, when you get a norm, when you get a norm from an inner product, okay, it will satisfy the parallelogram law. Okay, so you can actually, you can define some norm actually which and you can show that this norm don't satisfy the parallelogram law. Okay, so that is how you do, that is how you prove that few norms are not coming from your inner product. Okay, for example, this is a, I guess this I guess soup norm. This is how we define soup norm.
Yes, sir.
Yeah, this is not coming from any inner product. Okay, there is no inner product, so that you can write this as square root of xy, inner product with xy. There is no such inner product for which you can write this. Okay, for all x comma y in R square. Okay.
Sir, is it easy to prove this?
It's not difficult. Okay.
Okay, sir, I'll try and let you know.
The thing is, the idea is parallelogram. Okay, so so first you have to show that the whatever norm is coming from an inner product, they satisfy the parallelogram law. Okay, and next thing you have to show that this norm doesn't satisfy the parallelogram.
The parallelogram law means the triangle inequality.
No. This what norm of
linearity.
No. Parallelogram is basically norm a square, norm b square is norm a plus norm b whole square. Yeah. Okay, so yeah.
Just can you just write in the what it is, the parallelogram, so that it stays there, so that I could come back to it.
Yeah, as far as I remember,
is it related to addition of
clear?
Okay, sir.
Sir, isn't it the same?
Sorry?
Is it different, this one?
Which one?
The two-side expression? Only the bracket.
No, this no, what I'm
Okay. Sorry. Yes.
Yeah.
I missed it. Let's proceed. Yes.
Yeah, it's okay. Sorry. I guess I'm doing some mistake over here. I guess, yeah, it's not true. This is okay. This part is true. Okay, this, I guess this is not true.
So it is, I think, 2 into that
yes.
norm of A equals to D minus VR.
Yeah. Now I guess it's fine. Yeah. So A is a vector in your vector space P. Okay. A and B are the two vectors in your vector space B, and this is what the parallelogram law is. Okay. So it says that norm of A plus b square, and norm of a minus b square is basically 2 times norm of a square plus 2 times norm of b square. Okay. So you can show that actually if a norm is coming from an inner product space, okay, if a norm is coming from an inner product space, it will satisfy this condition. Okay, but you can show that this norm, this soup norm, actually will not satisfy this condition. Okay. Is it clear, Prithvi?
Yes, sir.
Yeah. So
now, sir, if we, it is not obvious that the norm would be defined as the okay, so norms can be different. From this, we can conclude that the definition, there's something wrong with the definition provided for orthogonality or orthonormality, on orthonormality in particular, because it should be the, say, a vector v1 and v2 are orthonormal, then we should have
what do you mean by v1 and okay, this as I said they are orthonormal. Okay.
Yes, sir. Yes, sir. Or okay, then we must have the inner product of v1 with itself should be 1.
Sorry, v1 with itself should be 1. Yeah,
Yes, sir.
orthonormal.
But in the definition it was given norm of v1 should be 1.
Yeah, that is the same thing, right?
No, that is the reason I'm asking you. How is it same? Because norm can be anything.
No. Norm with respect to the norm, whatever you are getting with respect to that inner product.
That is what was not explicitly mentioned, and this has caused many confusion throughout many individuals who have tried to solve a few activity questions and were confused. There was a set of activity questions which required the use of this property instead of the norm being 1, and many of the people got it wrong.
Here specifically I have the same doubts related. So
is it like, because I guess in the lecture, like it's clearly I guess mentioned like whatever inner product.
Sir said the norm is equals to 1, which is equivalent to inner product being 1. And
yeah, so basically that is what is basically, see, when you have an inner product on the space, the norm, okay, like if some inner product, see, when we are specifying the inner products, clear, like where whatever norm we are getting, that is basically from, okay, I understand your point, but okay, so when actually we are specifying inner products, then you should assume that whatever norm is given on that inner product is basically coming from that inner product. Okay, so
here
the inner product that will be
what I was
sorry.
What I was asking is, so given that a defined inner product is there, so norm for any of these
my question is now, okay, I was talking about projection, then now I'm discussing this. So is it fine, or do you want me to go back to there and discuss that particular thing?
I'm just coming to the norm part alone, sir.
Okay.
So we have a defined inner product for vector space. So this inner product being defined, my norm will be whatever be the inner product defined. My norm will be inner product of a vector with itself. Right?
Yes, true.
That will be the norm for that. Okay, thank you.
Now, sir, this
if the inner product is given, then you can assume that this if this is given.
Yes, yes.
If it is not given, and I'm talking about some norm, then it can be any arbitrary norm. Okay.
Yes, so if it is not given, then 1 second, sorry. So if it is not given, then we can go back to the standard dot product, right?
No. Okay, like
for norm, I'm saying we can go and do that v1 square plus v2 square, whatever be the dimension. If the inner product is given, but the norm is the definition for norm is not given, then we can take the standard one, right? v1 square plus v2 square plus whatever be the dimension.
It's basically in this course, if if a inner product is not given, yeah, it's basically the standard inner product.
Standard one.
Yes.
So what I think is a particular distinction should be made regarding length, norm, and the product of the inner product. Basically, inner product of a vector with itself. Otherwise, there's a lot of loopholes, and people may.
Okay, so let me. Okay, just a minute. So can you tell me some question where actually it's creating confusion?
Activity 8.2. Question number probably the last one, last set. Let me check. 8.2 question number. Yes, sir. Last one. 8, 7, and 8.
No, what is okay? Like here, actually, there is you don't like. Yeah, so I guess here even you don't need norm, right?
So we need norm as in order to find the orthonormal basis, but here norm has to be defined in terms of the product of the inner product
So
of the
inner
vector.
product is given here, right? It's not like that inner product is not given.
But actually we have been the reason I'm asking for a particular distinction because the norm has been used the what do we say, the notation of the norm has been used in analogous to the notation for length, and people are often doing the calculation of length as a norm and getting it incorrect.
Okay, I got your point. Yes.
So that will happen if I think Pritham, is that will happen if the inner product is not defined specifically for that. Is it defined specifically? Otherwise, we can do the standard one, right?
Yeah. If the inner product is not given, then you can take the standard inner product. If the inner product is given, then basically the whatever norm you should use with respect to that inner product. Anyway, yeah, like it's okay. It's basically only one thing we have to write that consider the norm which you are getting from the inner product. Okay,
so why don't we remove the norm from the definition itself? Does it give any additional information?
Sorry.
Why don't we remove the norm from the definition of the orthonormality itself? Does it give any additional information? Instead of writing a norm of V equals 1, we may write inner product of V with itself as 1, and we just remove norm from itself, from the definition.
No, like orthonormality, it's more or less it will give you some kind of unique. Orthonormality will give you some kind of uniqueness, right? It's you are in the end you are getting some unit vectors.
Yes, sir.
Yeah, so it's more or less it's some kind of uniqueness is there because in each direction you have a unique vector whose length is 1, right?
Yes, sir.
Yeah, so but if you just simply give some orthogonality, so if you put simple orthogonality, then you will lose the.
No, sir. That wasn't what I was saying. I was saying that there are two conditions. First of all, say write a set V1 and V2. Now we are claiming that V1 this set will be orthonormal if V1 dot V2 V1 with inner product of V1 with V2 is equal to 0, and as defined in the lecture, mod of Vi, norm of Vi equals 1.
Yes.
This is how it is defined. So my point was, instead of writing norm of Vi, why not we write inner product of Vi with itself is equal to 1?
They are basically the same thing.
Yeah, but the
I understand your point that it's creating confusion. Okay, but okay, so the thing is
but Pritham, I think sir showed that, right? After that, the norm sir showed this point, right? Vi the inner product equals to 1. From that, I think so.
So the thing is, okay, so the thing is, it's since we are talking about the length, okay, so when the speciality about the inner product is basically the length of each vector is the speciality about this orthonormal basis, that each vector in that orthonormal basis has length 1. So I guess if you write this this notation is more accurate, okay, writing instead of writing this one. You see, more or less they are the same thing, right? They are the same thing, right? See, this norm of vi is basically this, and if this is 1, then certainly this is 1, and if this is 1, then certainly this is also
1. But the condition is that the algebraic expression should be equal. That is where I am reaching.
Which algebraic equation
should the norm should be defined as the square root of the inner product.
Yeah, so if the inner product is given, okay, so then that is how you define
that
a
is
norm.
We are assuming, right?
Yeah, true.
But
that is correct.
Will not be the case. Suppose I'm defining norm as the mod value of
then okay, then what is the point of giving that inner product? My question is, if you are if some inner product is given and some norm is given, and if you take some arbitrary inner product, what is the point of taking that inner product, more or less?
Okay, sir.
Yeah, so at the same time, whatever you are saying, I guess it's I agree with that, but there is no point of repeating the same thing again and again and again. But yeah, so we'll try to mention mention this one in a single question, or maybe in some in solve with us thing. Okay. So
also, sir, can you pen down the proof of the triangle inequality of the inner product to be satisfied?
Yeah, it's okay. See, this is a standard proof. Okay, you okay. So again, it will take some time. Okay, it's basically, if you search it in any place, you will get it.
Okay, sir, I'll look for it then.
Yeah.
Okay, sir. Then after this, I just have a few questions from the activities.
Okay, so let me now at least complete this projection thing. Okay, so I wanted to do something related to projection. Okay, so I guess so I want to project this vector 1, 2, 3 on W, and a basis of W I guess is 1, 0, 0, 0, 1, 0. Yes, this is basically XY plane. The span of this set will give you XY plane, and W is XY plane. So I want to find projection of 1, 2, 3 W, right? Okay, so how I have to do it? I just okay. So before I gave you the formula. V is basically what? V times Wi into Wi summation y 1 to n, and W1 to Wn is a basis, orthonormal basis of W. So we have a orthonormal basis. So this is W1, this is W2. So certainly this is a orthonormal basis. So then what we need to do? We need to first consider W1. So the inner product of 1, 2, 3. This is my V. V is 1, 2, 3. And then I have to consider W1. And W1 is 1, 0, 0. Again, I have to multiply with. So this is a scalar, right? I have to multiply with 1, 0, 0. Again, I have to do the same thing with respect to W2. Inner product of 1, 2, 3 with 0, 1, 0 into 0, 0, sorry, 0, 1, 0, right? So what is this value?
So it is the first option, I think. 25 by 49.
It is 1, 2.
Yeah.
1, 2, 0.
Yeah, oh, this is basically one. I'm asking about this one.
Okay, I got it.
So this is basically 1, 0, 0. I guess, yeah, this is 1, 0, 0. This is
1, 0, 2, 0.
0, yeah, 0 to 0. So this is 1, 2, 0. Okay, it's basically, it's quite intuitive, right? Because if you are if you have a point 1, 2, 3, and if you are projecting on XY plane, then you should get 1, 2, 0, right? Because, yeah, so okay, let me do one more question. Maybe this one with respect to some non-standard inner product. I'm going to solve question number 6. Okay, so 8.3, question number 6. Okay, I guess I have to do maybe slightly more calculation on this, but let me do it. So some inner product is given. So some inner product is given on R square. So how we have defined this inner product? Let me mention the inner product.
So which question is this?
Question number 8.3. Question number 6.
This is the usual product.
Usual dot product, sir.
Oh, okay. So I thought it's with respect to some different inner. Okay, I was thinking about the inner product given just before question number 4. Okay, sorry.
Sir, can you explain question number 5 in that? Just the projection part, that x minus projection of x. That is used in question number 5, I guess. Can you explain?
No, okay. Question number 5. It's basically okay. So what? So now what you want? So what you want me to do? Question number 4, 5, or question number 6?
4 I have done, but question number 5, like 8.3, question number 5. Can you explain that?
If you have done question number 4, then certainly you can do question number 5. See what you need to find a vector which is perpendicular to 3, 4, right?
Yes, sir.
So
from question number 4, the first option is correct. So I'm also like 25 by 49 and got that. That is the projection in the of 1, 2 x in the direction of 3, 4.
Yeah. So
now the second part is talking about the projection perpendicular to the direction of 3, 4.
Yes.
So from that, the previous thing that you showed, like if x, the projection of x, then perpendicular is the x minus the projection of x. That is the perpendicular projection, right, sir?
No, what do you mean by perpendicular projection? Like no, that is a different thing, right? I was just saying that this if you are taking this vector and you are taking the difference between its projection, okay.
Yeah.
So this is basically perpendicular to W. This what actually it's basically saying, this vector is perpendicular to this space W.
Okay, so sir, can you do that? Like how to do this question 8.5?
8. See, if you have done question, okay, I don't see any, because if you have done question number 4, then there should not be any issue, because see, in question number 4, what you did, find the projection of x in the direction of 3, 4,
yes,
right?
Yes.
So for question number 5, what you need to find? Find the projection of x in the direction of perpendicular to 3, 4.
So I find any vector like perpendicular to 3, 4, and then to the projection.
Then you project 1.2 in the direction of that vector. Is it clear? You just need to find a vector which is perpendicular to 3, 4. That's all.
Like any vector, and I can
obviously you have to normalize it. Okay, so because you need to take a orthonormal basis, right?
Okay.
So if you take any vector and if you normalize it, always you are going to get a unique vector. Okay. Is it clear?
Sir, like I am having this confusion, like if any vector that is, say suppose the vector is AB, and I am doing this with respect to 3, 4, then I can use the orthogonal condition that inner product will be equal to 0.
Yes, true.
So from there I get a condition with respect to M and N. And where is the second? Like I need the second equation.
What do you mean by second equation?
Like A, after that I have to find A and B, right, sir? So I get the inner product of that with respect to 3 and 4 equal to 0. From there I get an equation with respect to 3 and 4. A and B. So like to find explicitly.
There are infinitely many such vectors, so you won't get another condition, and hence you won't get a unique solution. You have to take any one solution and work with it.
Okay. So
but any solution you get, if you normalize it, it will give the same
vector.
Vector.
If you normalize it, then certainly it will give you a unique vector, right?
Yeah.
Obviously. Yeah.
Okay.
So
okay.
So my point is, okay, if I take a vector, any vector in this line, okay, not this line, in particularly in this direction. So if I normalize this vector V, then obviously I will get a unit vector in this direction. Similarly, if I take some W and if I normalize it, obviously I will get the same thing. Okay, so W by W non is basically same as V by V non. Okay, because in this direction, this unit vector is unique, right? Because see W is basically a multiple of V. Okay, so if I take 1, 2, and if I take 2, 4, and if I normalize this vector, what I will get? 2 square root of 5. Okay, and also if I normalize this vector, then both are same, right? Hello.
Yes, sir.
Yes.
Yeah. So when you will normalize it, basically you are going to get the same thing. Okay. But I guess you have to consider the direction. Okay, because if I take the opposite direction, then I will just get the opposite negative vector. Okay. So probably you have to do for both the cases. Okay. For example, you have to take vector 1, 2 as well as this, I guess, -1, -2. Okay, so basically you will get two vectors in different directions. Okay, is it clear?
Okay, so I'll try it out then.
Yeah.
So can there exist a matrix the rows of which form an orthogonal set but not orthonormal set be an orthogonal matrix?
Sorry, be an orthogonal matrix?
So can there exist an orthogonal matrix the rows of which are form an orthogonal set but not orthonormal set?
No, that is not possible, because so if this is identity, then also identity. So
yeah, so I was thinking
that
that
okay, so don't okay, so there is a difference, like there is a notion of orthogonality even in the case of non-square matrices. So in those cases, so you may get different, you whatever you're saying, you can get a counter example, like where rows are orthogonal, maybe the columns are not orthogonal. Okay, but certainly here we are basically, the way we have defined orthogonal matrix are basically square matrix. Okay, so in case of square matrix, it's not possible.
So we may have an M cross N matrix and transpose would be N cross M, and they would end up giving us M cross M identity.
Yeah. In those cases, so there is actually you can define orthogonal matrix for non-square matrices also. Orthogonality. Okay.
Yes, thank you, sir.
Yeah. Okay, so so I was doing something. So okay, so let me do this question number 6. Okay, question number 6. Okay, I thought it's given with respect to some different inner product. Okay. So question number 6. So the basis is 1, 2, minus 1.
1 to 1.
Sorry. 1 to 1. The next one is 0. I guess
minus 2, 0, 2.
Minus 2, 0, 2. So it's given that it's a orthonormal basis. I guess it's orthogonal.
It is orthogonal.
Orthogonal basis of W with respect to the standard inner product. Then what we need to find? We need to find the
projection of 1 to 3.
Yeah, projection of 1 to 3 on this space W, and this space W is generated by these two elements. Okay, so since the orthonormal basis is given, we have to convert it into some since orthogonal basis is given, we have to convert into a orthonormal basis. Okay. So for that, we just need to divide the norm, right?
Yeah.
So if I divide the norm, what I will get 1 to 1 divided by 4 and minus 2, 0, 2 divided by square root of 8. Okay, so this is a orthonormal basis for W, and I need to find the projection of this vector on W, and then so basically the same formula I have to use. So this is my W1, this is my W2. So I need to find projection of this vector 1, 2, 3 on this space, and this is a orthonormal basis of W. So first thing what I need to do, I need to take 1, 2, 3 inner product with 1, 2, 1. W, and this is 1, 2, 1. Right, this is as you remember, this is V1 W1 times W1, right? And same thing I have to do for the another vector, that is W2 times minus 2, 0, 2 square root of 8 times 1, minus 2, 0, 2 divided by square root of 8. So so this thing I can write. So if I can take 1 by square root of 6 out, and I can multiply with this, so I can get 1 by 6. Okay, I'm using the property of inner product. So if I take this 1 by square root of 6 out, and if I multiply with this 1 by square root of 6, then I'll get 1 by 6. And this inner product is what? 1, 2, 3, yeah. 3, 4, 7, 8, yes. So this is 1 by 6 times 8 into 1, 2, 1 plus again this is 1 by 8. This is minus 2 plus 6. So this is 4 times minus 2, 0, 2. And then you do the multiplication. Maybe it's basically what 4 by 3, 1 to 1. This is half. Half, if you want to remove, then basically you will get minus 1, 0, 1. And if you add these two vectors, then you will get your projection. Okay. So the main thing is to find to get the projection vector. You have to get a orthonormal basis. So once you have a orthonormal basis, then it's basically this computation. You have to do some computation to get your projection vector. Okay, this part is clear, right? How actually we are getting this projection. Any doubt from this part?
No,
sir. Sir, regarding the thing that you are writing, like x minus the projection of x. Suppose there is a vector x, okay, and the projection is projection of projection of x is there, and the angle is basically theta between them, right? Cos theta that we take.
Projection, you have vector v, and
yes,
you have projection vector of v on w. Yeah.
Yes. Now the angle is basically theta in between them.
Okay.
Right. So then the thing that you are writing, like v minus projection of v onto w, that is basically the perpendicular, right? From
yeah.
So
this is perpendicular to w.
So the direction is towards v, right, sir?
No.
Because if I'm doing
if this projection of w is 0, then you can say that the direction of this vectors is towards v.
Sir, what I'm saying that the projection of v, that is a vector, plus this v minus projection is equal to v. So there is some vector addition going on, right, sir?
See, this is a vector. V is a vector.
Yes, sir.
So what is your question now? You are saying the direction of v and direction of v minus projection of v are basically same. That is what you are saying.
No, sir. No, sir.
Okay.
I'm talking about that v minus projection of v is projection of v is in a direction, and v minus projection of v is something that is perpendicular to the projection of v.
Yes,
so
yes. True. You are,
and I am saying that the direction is towards that vector v, that perpendicular that is going.
See, projection of.
Sorry, I'm saying perhaps in the wrong.
This is in w. Manner. This is in w, right? Projection of v on w is basically in w. Okay.
Yes, sir.
So this statement I agree that projection, this vector is perpendicular to this vector. That yes. I agree, but I don't think.
What I am saying is that the projection of v plus the v minus projection of v is equals to this v, like it's a vector addition, right?
Yeah, that is true, right?
Yes, so that's what I'm saying. Like so, in that triangle that Sir has drawn, actually, so that is the perpendicular is the projection v minus projection of v, right? I'm just talking about the diagram.
Yeah.
Okay. Yes. Okay. Got it.
Okay, so the next thing I want to do, maybe I just want to give you some idea about this Gram-Schmidt, or maybe I will compute one one example
Yes,
using
sir.
the, sorry?
Go ahead, sir. That's good.
Sorry, Hari?
No, sir, nothing. So just go ahead, sir. That's what I'm saying.
Okay.
Yeah.
Okay, so the next thing, so this, how actually we can get a orthonormal basis. Obviously, first I must have a inner product space. Okay. So V is a inner product space. Okay, V has some inner product structure, and I want to find a orthonormal basis using any arbitrary basis of this vector space P. Okay, suppose so. Okay, so the process is first you have to take a basis. Okay, so let's say this beta, which is V1, V2, Vn, is a basis of V. This is first you have to take a basis. Okay, I can take some basis, you can take some other basis, and in the end we may get two different orthonormal bases. Okay, but our aim is to find a orthonormal basis. It doesn't matter whether they are different or they're same. Okay. So the first you take a basis, and the process is W1. You first take, so simply we're denoting this V1 as W1, and as you know, in orthonormal basis you want all the norm of all the vectors to be 1. Okay, so we don't know whether this V1 is the norm of V1 is 1 or not. So first thing we have to normalize it. So E1 is E1 divided by the norm of U. Okay, so then my first vector in my orthonormal basis is basically the first vector in orthonormal basis. So B dash is, I'm denoting B dash as the orthonormal basis that I'm getting from B. Okay, so the first vector of this orthonormal basis is U1. Okay.
So it should be V1 by norm of V1.
Oh, sorry. So this is my first vector, or better to write W1.
Yes, sir.
By norm of W, because I'm simply, I'm taking the first vector and I'm denoting this V1 as W1. Okay, and then I'm dividing the norm of W1 by in that vector W1. Okay, so I am getting a new vector U1. So U1 is the first element of my orthonormal basis. Okay. So then I need to compute the second vector. Okay, I want to compute a vector U2 in my basis such that U2, the norm of U2 is 1, and as well as the inner product of U1 and U2 is 0. So I want a vector U2 such that the norm of U2 is 1 and inner product of U1 and U2 is 0. That is what my target is. Okay. So how we define? So next you define W2 as V2, the second vector V2 minus V2 inner product with U1 times U1. So till now we know U1, we know V1, V2 and Vn. Okay, so using that I am constructing W2. Okay, and you can see, you can check that inner product of W2 with respect to U1 is 0, right? If I take the inner product of W2 with respect to U1, then I will get 0. Is it clear how actually the inner product of W2 and U1 is 0?
Yes, sir.
Yes. But also we want one more condition, that the norm of so certainly we cannot take U2 as W2. Certainly U2 is perpendicular to U1, but we don't know whether the norm of W2 is 1 or not. So for that I have to divide W2 by its norm, which I will denote it as U2. So U2 is W2 divided by its norm. So then U1 is the first element and U2 is the second element of my orthonormal basis. Okay. So then similarly, so my next target is I want an element U3, so that the norm of U3 is 1. That is the first condition. And the second condition is U3 is perpendicular to both U1 and U2. Okay, so that is my second condition. So I want to construct an element U3 such that the norm of U3 is 1 and U3 is perpendicular to U1 and U2. Okay, so next how I will construct. So then I will first define W3. So what is W3? W3 is same process, V3 U1, inner product of V3 U1 times U1 minus V3 inner product of U2 times U2. And again, you can check that the inner product of the W3 with U1 is 0 and inner product of W3 and U2 is 0. But again, we cannot take W3 as U3 because we don't know whether norm of W3 is 1 or not. Okay, so for that I have to divide the norm of W3 by W. So what is U3? U3 is W3 by norm of W, right? Then I got the third element of my orthonormal basis, U2, U2. And if I will follow the same method, then similarly I can get the nth element of this orthonormal basis. And how? So this Wn is basically Vn minus Vn times E1 into U1 Vn times U2 into U2 and up to Vn times E1 into U1. And again, you can check that this Wn is orthonormal to, it's not, sorry, orthonormal, it's perpendicular to U1, U2 up to Un minus 1. But again, we don't know whether norm of Wn is 1 or not. So for that, I have to divide Wn by its norm. Okay, and which I will denote it as Un. So then if I'll do, then I will get basically a orthonormal basis. See, this orthonormal basis we are getting from this basis. Okay, if you pick some different basis, then you may get some different orthonormal set. Okay, so let me do one example.
No.
So this process is clear, right? How actually we are calculating the orthonormal basis.
Yes.
Yes. Yeah. So, okay, let me do one example. Let's say maybe.
So, 8.5 question 4, I think.
Okay, 8.5 question 4. No, okay, that is a different question. It's basically it's saying so some orthonormal set is already given. Okay, I'll discuss that one. Okay, but let me do some proper example.
This is just we have to find the dot product to be 0, right?
Yeah, it's basically there are multiple ways, but I guess that is the easiest way to solve this question. So you need to find some vector which is orthogonal to B. Okay, so more or less you have to solve two system of equation.
Sorry, sir. 8.4 question 4.
Okay, 8.4.
8.4 question number 4.
Yes, that is actually it's a question which we can do using Gram-Schmidt. Yeah, this is a proper question, but it's going to be
very big.
Yeah, I have to do a lot of calculation. Okay, so V1, V2 and V3 are given. So I need to find a orthonormal basis. So I need to find a orthonormal basis using these three vectors. So these vectors are given. V1 is 1, 1, 1, 1. V2, this is V1. V2 is 1, 1, 1, 0. This is V2. V3 is 1, 1, 0, 0. This is my V3. Okay, so first thing I have to do, I have to find W1. Okay, that is what we have done here. So my first thing I need to find, okay, W1 is basically V1. So first thing I have to find U1, and U1 is what? W1 by norm of W1. Okay, so here W1, which is basically V1, which is 1, 1, 1, 1. Okay, so then U1, what is U1? U1 is W1 by norm of W1. What is that? 1, 1, 1, 1 divided by square root of 4. Okay, yeah, so this is 2. So 1 by 2 times 1, 1, 1. So this is the first element of my orthogonal, not orthogonal, orthonormal basis. Okay, so the next, my next thing is I need to find W2. Okay, so what is W2? W2 is, how I define W2? W2 is V2 minus V2 inner product with U1 times U1. Okay, so I know U1. Okay, I know V2. Okay, I just need to replace the values. Okay, so V2 is 1, 1, 1, 0 minus V2 is 1, 1, 1, 0 times U1, and U1 is this half 1, 1, 1. Again, this is again I have to multiply with E1, right? Half 1, 1, 1, 1. So this is my W2. Okay, so let me compute what is W2. 1, 1, 1 0. If I take this half out, and again if I multiply with this half and this half, I'll get 1 by 4. And if I multiply this, if I take the dot product of this vector with this vector, then I should get 3 times this vector 1 1 1 1. Then what I will get now? This is
2 by 2.
Yeah, so this is I guess this is 1 by 4. Yeah, basically 1 by 3 minus 4, right? So this is 1 by 4. This is 1 by 4. This is 1 by 4.
Minus 3 by 4.
Yeah, minus 3 by 4. So what is the norm of this vector?
Root over 12.
Root over of 12.
Yes, sir.
You're saying norm of this vector is root over of 12.
Root over of 12 divided by 2. That is.
Root of 12 by 4. 12 by 16.
1 by 16. 1 by 16 plus 9 by 16. It's basically 2 by 12 by 16 square root. So it's basically what, 3 by 4? It's root 3 by 2, right?
Yes, sir.
So this is my W1, right?
Correct.
Not, sorry, W2.
Hmm.
But how we can get U2? Our next target is to find U2. Okay, so U2 is basically W2 by norm of W2. Okay, so I know W2. I just need to divide W2 by norm of W2, and norm of W2 is root 3 by 2. So if I do it, then what I will get? 2 by root 3 into 1 by 4, 1 by 4, 1 by 4 minus 3 by 4. And this is nothing but what? This is 1 by 2 root 3, 1 by 2 root 3, 1 by 2 root 3 minus 3 by 2 root 3, right?
Yes, sir.
This is U2. Okay. So our first vector is this E1 is half 1 1 1, and this is our U2. Okay, Pritam, I guess you suggested me this question intentionally.
For?
I guess you suggested.
Why sir? Why sir?
No, because this is a lot of calculation. Okay, so that's why I'm saying.
No, sir. Even in the first set of questions where there were 3 vectors, the same amount of calculation is there.
Okay, because it's I'm also feeling like, yeah, I'm doing a lot of calculation. Okay, so okay, so the
basically
next
when the basis consists of 2 items, that is 2-dimensional, then the calculation will be lesser.
Yeah.
In most of the questions we have 3-dimensional.
Okay. So okay. Yeah. This is 4. Yeah, that is actually, it's even near. So W3. So okay. So now we're done. So we're done with U1 and U2. Okay. So our next target is to find U3. Sorry, W3. And how we can find? Sorry.
I think that we can skip, right?
Okay. Yeah. So then it's good. Okay. At least for me. Okay.
Yes,
So
we can skip.
okay. So then you can get some vector W3, and whatever you will get, you just take U3 as W3 by norm of W. Okay. So once you have computed U3, then the orthonormal basis is U1, U2, and D3. And this basis you are getting from this V1 and V2 and V3. Okay, and I'm repeating that if you start with a different basis, you may end up with a different orthonormal basis. Okay, so it's not like that. Whatever basis you are taking, you will always get a unique orthonormal basis. Okay, for different basis, orthonormal basis will be different. Okay. Okay, so let me now. Okay, so I guess. So, do you want me to recall in some other thing apart from this?
Yeah, I have some questions.
Basics of rotation.
Basics
orthogonal
of
rotation. Orthogonal rotation.
This okay. Okay, one more thing. Is it the last session of week 8?
That was the last.
No.
Yeah.
This is the last session of week 8, or this is the
first session.
This is the first session.
Yes, first
class.
sir.
Okay, so okay, then keep this at least for the next session. Okay, so okay, you ask that question in the next session. Okay, so you want me to complete whole week in one session?
Yes, sir. Yes.
Okay, so no, the thing is, why actually I'm saying I if you have some doubt, then actually I want to discuss.
If you explain the concept,
the
then
basic concept, sir. Yeah.
No, so no, actually what I want to do, see, it's already more or less 12. So what my plan is to solve some of your doubts. Okay, so because I've not discussed much of your doubts from the activity part. Okay, so that is what I want to do for maybe some next.
Okay.
Yeah, so
8.2 question 4.
Because yeah, so the thing is, I guess you have 2 more sessions. Okay, 8.2
question 4. So
yes.
I guess there's an easy proof, or there's an easy way to look at it, but I did the proof for 2 cross 2 and it was quite lengthy. So can you prove it?
Right?
Determinant? Is it determinant or?
No. If the matrix is orthonormal, okay, this.
So which question?
This question 8.2, question number 4. Okay, so it's saying that determinant. Okay, the option is determinant of a 3 cross 3
orthonormal vector. Matrix formed by orthonormal vector is
okay. Yeah, it's basically it's saying determinant of a 3 cross 3 orthonormal matrix, right?
Yes.
Is plus or minus.
It may not be 3. Why would it be? Okay, 3 cross 3. Yeah, R3. Yes, sir.
Yes. So then it will satisfy this condition, right? See, this A transpose A is identity, right? I'm basically it's there is nothing special about this 3 cross 3. Okay, you take n cross 3. Okay, so it will satisfy this condition, right?
So how can we claim that?
Which one?
That it will satisfy this.
See, this is a orthonormal. The columns are orthonormal, right?
Yes, sir.
So if you take the transpose, okay, this is okay. Let me do it for this ABCD, right?
Yes, sir.
This the inner product of AB times CD is basically 0, right?
Yes, sir.
And inner product of AB with AB is Yeah. So now if you multiply, let's say SC and BD, right? What you will get now?
AB dot AB
is 1, right? Because orthonormal, it's a orthonormal vector. AB,
yes,
this
sir.
AB is a orthonormal vector, right?
AB 1.
Yeah, so then
1001.
1001. Right?
Yes.
So you can do it for any 3x3 or maybe 4x4. It's true for n cross n. Okay, it's just giving you. So now you apply determinant. So determinant is 1, right?
Yes, sir. That means determinant of A whole square is 1.
So then what I am just applying the property, the multiplicative property of determinant. This is 1. And do we know that determinant of A transpose and determinant of A, they are same, right?
Yes, sir.
So this is same as determinant of A square, which is 1. So that means determinant of A is plus or minus 1.
When it can be minus 1, sir? Where?
Sorry?
Is there a matrix like where it can be minus 1?
Yeah. So you take this matrix, right? Minus
1 0 0 minus 1. Yeah.
Yeah, this matrix, right? This is also a like here the vectors, the column vectors are orthonormal, right?
Yes. Okay.
So but how can it be minus 1, sir? Because 2 squares are there.
Which one? Sorry,
like minus 1 0 0 minus 1 that you are telling, that one.
This
so
one,
that is
right?
actually, yes, that is actually A square plus B square, right, sir? If
No.
like in the original dot product I'm talking about.
No, I'm saying
the
dot product is 1. I'm talking about, see, actually he asked me to give an example of a matrix, okay, which satisfy this condition, okay, the condition given in the question, but the determinant of matrix is minus 1. So determinant
okay. So that is a separate example, like
yeah. So determinant of this matrix is minus 1. The column vector, they are certainly orthonormal. Okay, so I guess that gives you the solution of question number 4, right, Pritham?
Yes, sir. Now, sir, suppose we are given a matrix, the vectors of which, the rows of which are orthonormal. Can we say the column vectors will be orthonormal too? If yes, then how?
Yes. Okay. So the thing is, again, the same trick you have to use. Okay. So the thing is how it. I guess there is one question in maybe mock or maybe quiz 1. It says that if AB is identity, that means BA is also identity, right?
Yes, sir.
So if you know that A into A transpose is identity, then you can say that A transpose A is also identity, right?
Yes, sir.
So you are saying you have a matrix A and the rows of the matrix are orthonormal, right?
Yes, sir. Yes, sir.
So let me again do it for 2x2 matrix. You can the same idea you can generalize. Okay. So AB CD, right? So this is my matrix and I know the rows of the matrix are orthonormal. So that means AB dot product with CD is 0 and norm of AB is 1 and norm of CD is 1. So what I have done here, I have computed A transpose, right? I multiplied A transpose with A in case of column. So in case of row, I'll do the reverse. Okay. So now you take A into A transpose. What is that? AB CD this is AB, CD, right?
Yes, sir.
So this is identity.
Yes, sir.
So if this is identity, so that actually, so this one I'm getting from the given information that rows are orthonormal, right? So
Yes,
if this is identity, I can say that A times A is identity, right?
Yes, yes,
So
sir.
once A transpose time A is identity, then again you can say that the columns are also orthonormal, right?
Yes, sir. Yes, sir.
Yeah. So
basically, suppose we are given the matrix representation of our orthogonal transformation, then the matrix will be orthogonal matrix, and we know that the vectors has to be orthonormal, and then we can say the column vectors are also orthonormal.
Yes.
Okay.
Okay. So any more questions?
Sir, could you please check solve with us question for the answer I get didn't match with the answer given?
Solve with us question number 4.
Yes, sir.
You need to find the projection vector, right?
Yes, sir.
Okay, just a minute. Let me write the question first. Solve with us question number whatever 3 maybe. Consider the vector.
That is 4.
Okay. So sorry. So I want to find the projection of this vector 1, 0, 1. Projection of this vector onto this subspace W. And what is W? W is a 2-dimensional subspace, and it's given by this equation, right? X, Y, Z, such that X minus Y plus Z is 0, right?
Yes.
Okay. So what is your orthonormal basis for this? Hello, Pritam?
Sir, 1 minute. I'm just checking.
110 and 10.
So I found the orthogonal basis. Then I used the formula. So I didn't find the orthonormal basis explicitly.
I guess it's easy to find, right?
Yeah, it's easy, but just it's that I didn't do. So the orthogonal basis is 1, 1, 0 and 1, 0 minus 1.
No, I'm thinking, okay, I'm making some mistake actually. Yeah. So first I was thinking, okay, how can this so I was thinking actually it's a XY plane. Okay, it's okay. It's completely, it's thinking something wrong. Okay, I was thinking 1, 0, 0 and 0, 0, 1 will be a basis. Okay, sorry. So say, I guess this is a basis. Let's say 1, 1, 0. This is a basis, right? This and yes. 0, 1, 1.
1.
Yeah. This is a basis, okay, of this space. So this is ortho. Okay, this is a basis. Yeah, true. But this is not an orthonormal basis. Okay.
No, sir. It's orthogonal.
It's even not
No,
orthogonal.
no, sir. It's not even orthogonal.
Orthogonal, yeah. So any example? Okay, again, if you have computed it, then I'll do it. Otherwise, I have to go to this Gram Smith.
I think 0 minus 1 1 will no, that also will not be. Sorry.
No, you are saying 0. No, if I take 0 in the first coordinate, then yeah, certainly it's not going to. What is your orthonormal basis, Pritham? Have you computed it or?
No, sir. I didn't complete it explicitly. I did.
Okay, so let me. Okay, then let me find the orthonormal basis first. Okay, so then only I can talk about this what a projection. So again the same procedure. I have to use.
If we take 0 minus 1 and 1 minus 1, 0 minus 1 and minus 1.
0 minus 1
and minus 1 and 1 1 0
1 1
1 0 0. This will be orthogonal, right?
No. The inner product is non-zero. This inner product. Yeah.
So okay, it's not.
The inner product of these two vectors is -1, right? So it's not 0 actually.
Okay. So you proceed. I'm thinking something.
Okay. So I want to find my first target is to get a orthonormal basis out of this base. Okay. So the first thing, okay, the first one is pretty easy. This U1 is basically what? 1 1 0, and I'll just divide this by the root. Okay. So this is the norm of this vector, and okay, it's basically two vectors, so even finding U2 is also not that difficult. So what is W2? W2 is
0 1 1.
Yeah, so 0 1 1 minus
dot product of 0 1 1
0 1 1 V2 0 1 1 dot product product of this with U1. So U1 is 1 1 0 times again U1, right? 1 1 0. So this is more or less 0 1 1 and square root to square root. If I take out, then what I will get? 1 by 2. This is
1 by 2.
This is 1, right?
Yeah, 1.
This inner product is 1, right? Yes. Times 1. This is 1 1 0. This is minus half
and 1.
Okay. So again, what will be the norm of this vector? 1 by 4 plus 1 by 4 plus 1. This is 3 by 2.
6 by 4.
This is half plus 1, right? This is 3 by 2.
Yeah.
So I have to take the square root. So then my U2 is what? W2 by norm of W2. So this is what is this? So this is basically root 2 by root 3. Right?
Yeah.
So I'm not making any mistake.
But if you keep it 6, it is the 2 can cancel.
Which one you are saying to keep it?
1 by, if it is root of 6 by 4 instead of root of 3 by 2.
Root of, you are saying 6 by 4. Okay, so then
you can get root 6 in the denominator.
Okay, so yeah. Okay, so anyway, I'm going to get the same thing. So this is basically what? Minus 1 by square root of 6.
Yeah. Yes.
1 by square root of 6, and this I will get root 2 by root 3, right? So this is my orthonormal basis. Now I have a orthonormal basis, and okay, so the orthonormal basis is what? Let me write 1 1. Okay, U1 is 1 1 0. 1 1 0 by square root of 2 minus 1 by 6. Oh, sorry, minus 1 is 1 by root 6 root 2 by root 3. Okay, this is my orthonormal basis of the vector subspace W. So my next target is to find what. So I was trying to find the
101
projection of 1 0. Yeah. So the projection of 1 0 1 onto this vector space W. So what is this? This is nothing but 1 0 1 0 1 inner product with this
1 1.
Yeah, V whatever this W1 you say, inner product with 1 1 0 square root of 2 again with the vector W1. Okay, so this is 1 1 0 root 2, and the same thing I have to do for this one. This 1 0 1. Okay, so then this is nothing but minus 1 by square root of 6.
1 by root of 6.
Okay, so what I want to do now, I want to just write this one. So this one instead of this one, I'm just writing this one so that I can take this out and multiply to get some. So so this is root 2 by root 3 times minus half 1 minus half 1.
You can take half also outside.
Yeah, if that is I guess it's better. So this is 2 root 3, and what I can write minus 1 1
1
2. Minus 1 1 2. Okay, so now this is root 2. I'll take it out. 1 by 2. This inner product is 1. So this is basically 1 1 0. So this part is this. So the next part is again I will take it out, root 2, this one from here and this one from here. If I multiply, I'll get 2 by 12.
12.
Yes. Hello.
So I said 12.
Sorry.
I said 12.
2 by 12, right?
Yes, sir.
So yeah. So then I can write it as 1 by 6. Okay. So again, this inner product is what? Minus 1 plus 2 1, right? This inner product of this with this.
Oh, sorry.
It's 1, right? Minus 1 plus 2. Yeah, it's 1. So with minus 1 1 2. Then what I'm getting, this is half 0 plus minus 1 by 6 plus 1 by 3, and what I will get 1 by 2 minus 1 by 6. What is this?
1 by 3.
1 by 3. 1 by 3, then half plus 1 by 6, 3 plus 4,
2 by 3.
2 by 3, 1 by 3. So this is the projection.
Yes, sir. Then the answer is correct.
Okay.
And so solve with no, sir. Let me see. Practice assignment question 7.
Okay, practice assignment question 7. Yes.
So I think the answer is not right.
You check the solution.
So I checked the solution as well.
So what is the mistake in the solution?
So I think the a plus b plus c component, it's coming out to be 7 by root 2.
Just a minute. Let me check the solution. It's basically there is nothing, because the matrix is basically it's given in the lecture itself. This is weak. Okay. Yeah, so question number 7, right? What is 3, 4, 5, 6. Yeah, 7, yes. Yeah, what is the mistake here?
And the a plus b plus c is coming out to be 7 by root 2.
7 by root 2.
Yeah, so that minus 1 won't never give a what to say, real number on the rational number on the numerator.
No, that certainly won't, but you are multiplying a rational number with a rational number, right?
Yes, sir, but the numerator irrational number with an irrational number, but the numerator of which is irrational too.
So then it will get cancelled, right? So you will get 6.
Okay, sir. Let's do it. A plus b plus c is 7 by root 2.
Okay.
Then minus 1. Now if I
what is A is given, B is given, C is given, right?
Yes, sir.
Okay.
Yes, sir. Oh, acha. Okay, sir. 1 minute. Okay. I'll check it. I'll get back to you. I'll check it.
So A is 1 by root 2, B is 1, C is 5 by root 2. So
Yes,
then you can just simply A plus B plus C minus 1. So there is a 1, B is 1. So B and 1 will get cancelled. So then you are left with 6 by root 2. So
got it, sir.
Yeah. Okay, so any other doubt from? Okay, okay, so if you don't have any other doubt, then yeah, I'll stop now. Okay.
Oh,
okay,
sir.
Yeah.
Sir, I have you did this quite early in the session. You said that dimension of V is equals to dimension of W plus dimension of that W complement of W. Yes, W4. So, sir, is the proof done in the videos? Like I have not watched, but I'm saying.
No. Proof is not done. Okay.
So can you just do it? Is it very hard or it can be done?
Okay, I have to think first of all whether it's hard or not. Okay, so.
Okay, sir. So then I will. You can do it in the next session, sir.
Okay, just let me think. Okay, so W dimension plus W plus W. Yeah. So okay. So the thing is, it's more or less see, it's more or less Gram-Smith, right?
So how?
So what, like this is B, right?
Yes.
Okay, so not certainly not this is B. This is I guess this is what we want to show. Okay, so
so do we proceed like the taking basis for W like that?
Exactly. We have to first take a basis of W. Okay. Otherwise, there is I don't see any other way. Maybe there is some. Okay. So first thing is you have to consider a W basis of W. Say W1 to W2 to Wm, right?
Yeah. Yes, sir. So this is the basis for W you're taking.
Right.
Okay.
So
then okay, yeah.
Then you can
So one thing I can tell that the first in the basis lectures you have said that any vector it can be extended to the basis for
V. Yeah.
Like you said like in one of the lectures, like it can be, it was there,
but
it can
okay,
be extended.
yeah. So yeah, that is true. But what I am trying to say that now you convert this basis, okay, into a orthonormal basis
using
Gram-Smith. Okay, you convert into a orthonormal basis. Okay. So I'll denote this as the same notation. Okay, this is a orthonormal basis of W, right?
Okay.
So you take a basis of W and you convert into a orthonormal basis. So this is a orthonormal basis. Okay.
Yes.
So now you can extend this to a basis of V.
Yeah. Yes, sir. So Wn plus 1, Wn plus 2 to W.
Wm
plus 1 to Wn, say.
N, right?
Yes.
Now again you convert this into a orthonormal basis. See, you will get the same thing if you follow the procedure, because already it's a orthonormal basis. Okay.
Yes.
So if you apply the procedure, you will get the same set of m vectors. Okay. Then you will get some vectors. Okay. Some other vectors here.
Yes.
Okay. Now this is
linearly independent.
Obviously this side is a basis, so this is a linearly independent. Okay. So basically this is your what? This is actually your W. This is a basis of W. Okay.
Yes.
And this is a basis of W. Pop.
Okay, so that is the W. Okay. Yeah. Okay.
So the thing is, yeah. So so using this, you can prove that this V is basically W plus W pop, right? Because certainly this whole set is a basis of W, right?
Yes, sir. And it can be separated into two independent subset.
Okay, so this is a basis of W, and this part spans W, and this part spans W pop. So then you can write this. Okay. This makes sense, right?
So for all Wi from W1 to Wm, 1 to n, the dot product of Wi with the other vectors is 0. So from this we can conclude that the other part is W pop, right?
Yes, true. This part is basically W pop. Yeah. Because if you pick any point from here, then basically inner product with all these vectors is basically 0. So that's why that is element of W. Okay. Okay,
So,
yeah.
for 8.5 question 4, you said that the easiest way to do it is dot product, taking dot product of the options with it, with the set. We can also use Gram-Schmidt, right? To get
Let me 8.5 question number 4, right?
Yes, sir.
Gram-Schmidt you can use, but okay, see the Gram-Schmidt is basically it's give you what, like no, for question number 4 you don't have to do it, like you just pick.
We don't have to do it, but we can.
No,
right?
even like the, yeah, basically see the Gram-Schmidt, what, so for Gram-Schmidt, as I said, it's depend on your the choice of the basis that you are taking, right?
Yes,
so
sir.
if you take a vector, then you may not get some vector given in the options, right? So
yes, sir.
So that is the problem with Gram-Schmidt. Okay, so
But
you don't.
but the vectors in the option will lie in the span of that, right? Whatever vector we get in this Gram-Schmidt.
Yeah, span, because using, if you apply Gram-Schmidt, then automatically you will get a basis, right?
Yes,
if you
sir.
choose a basis of R3, and if you apply Gram-Schmidt, then you are getting a basis, right? So all the vectors is certainly is inside that span of that basis.
No, sir, I'm not talking about, say the third vector is V3 and we see the span of V3. Then one of the options, the correct answer will lie in this span, right?
Yeah, no, what I am trying, okay, so what I'm trying to say, so V1 and V2 are given, right?
Yes, sir.
So bunch of vectors are given, some W1, W2, and you want to know which of the following are the orthogonal to these two vectors, right?
Yes, sir.
So how you want to start with Gram-Schmidt?
So for the Gram-Schmidt, I'm not using the orthonormal extension. I'm sticking to orthogonal part.
That is fine.
Yeah, so V1, V2 is already there. We will get a V3.
No, how you will get the V3? You have to pick some element from this.
So I'm completing the set.
You are extending this into a basis, right?
Yeah, not basis as per se. Yeah, but I'm looking at vectors which are perpendicular to both V1 and V2. It is becoming a basis because it is R3, but had it not been R3, then it would have given me a vector which is perpendicular to V1 and V2 both.
No, how that is what I am saying. How you will
using the Gram-Schmidt itself. So V3.
No, how you can use the Gram-Schmidt? See, the problem with Gram-Schmidt is, see, if you have V1, V2, V3, see, by applying Gram-Schmidt, you cannot get a set of cardinality 3. Right, you are saying I will get some vector V1, V2, and V3, and V3 is perpendicular to V1 and V2. That is not possible, because if I have a vector of n, if I have a set of n vectors, okay, if I will apply Gram-Schmidt, then in the end I will get a set of n vectors. So, but what you are doing, you are applying Gram-Schmidt to a set of 2 vectors, and you are saying you will get a set of 3 vectors. That is not possible, right? Mama. Hello.
Okay, sir. Okay, sir.
So to apply Gram-Schmidt, first you have to extend this into some basis, V1, V2, and V3. Then you can apply Gram-Schmidt. Okay. Then you may get some orthogonal vectors, V1, V2 dash, V3 dash. But you don't know whether this V3 dash is there in your options. Okay. So you don't know. It's depend on what kind of V3 you are choosing here. So that
one more thing. Suppose V1, V2 is given as it is given. Now I find a V3 which forms a basis. Basically I complete the basis, right? Now I can find a vector which is orthogonal to V1 and V2, right?
How? By applying Gram-Schmidt.
Yes, sir.
True.
I think
yeah. So
I'll come back in a moment, sir. Please excuse me, sir.
Okay. So then, so Pritam, I guess I'm done. Like we'll discuss maybe later. Okay. Or maybe you can post it in Discourse. So any other questions? Or okay, then yeah, then I'll stop the session.
Yes. Thank you.
Yeah, thanks.
Sir, are you there?
Yeah, so okay, so I was thinking to stop the session. Okay, so yeah, tell me, Pritam.
Okay, sir. Just open the slide.
Yes.
The working. Yes, sir. So suppose we have this basis. V1 and V2 are orthogonal, right? So suppose I'm constructing an orthogonal basis, right?
Yeah.
So V1, V2 will form the part of that orthogonal basis. Basically, V1 prime is equal to V1 and V2 prime
So here
equals to V2.
Here V1 and V2 are ortho. This V1 and V2 are not orthogonal, right? So
they are.
In the given question, they are not orthogonal, right?
They are.
Okay, then it's fine. Then
yes, sir.
Then you will get
yeah.
Then you will get V1, V2, and some V3 prime.
Yes, sir. Now, if I look at span of V3 prime, then options will fall in this span.
Yeah, because
correct option.
Yeah, because by coincidence, the dimension of R3 is 3. Okay.
Yes, sir.
If you cannot, if some two vectors are given in R4, then you cannot apply the same. Okay. If two vectors are given in R4,
because it may so happen that it lies in the span of the fourth vector.
Yeah, exactly.
But not in.
But whatever you are saying, you can do it over
sir,
here.
Even if it lies in the span of both vector or third vector, it will always be orthogonal to V1 and V2.
Yes.
So okay.
Then you have to see, you are doing lot of computation for that. Okay. So then you have to check.
Basically, I am looking at a general space where I'm not given the options and I can exploit things. So
Then
can be applied. I'm trying to figure out an algorithm.
Then Gram-Smith is the best way to do that. Okay. If you are doing in a general setup, okay, so then Gram-Smith is the best way to find the orthogonal conflicts. Okay.
Yeah.
But particularly for this question, whatever you are saying is correct. But okay, anyway, you can get it from the options. Okay.
Yes,
for this question, but as you said, for the general setup, it's better to do using Gram-Smith.
Yes, sir.
Okay.
Thank you, sir.
Okay. So then I'll stop now. Fine.
Okay, sir.
Okay. Thanks.